Hello, my name is Shin here. Here, I will explain design handling with variance precisely. This time, I will talk about the positioning of the content explained in this design as mathematics. The purpose of writing how to deal with variance is to improve the quality of goods and services by handling variances accurately. For example, results obtained using methods such as standard deviation, Monte Carlo method, and stochastic process have a certain amount of error due to the reasons described here. The reason for this is that existing numerical calculations do not have the ability to handle variance correctly. In fact, the variation is magnified by calculation. As a countermeasure, we proposed an arithmetic operation that has the ability to handle variance correctly. The mathematics mentioned in dealing with variance is called distribution arithmetic, which extends vectors into probability distributions in order to handle variance. For example, in the addition 1 plus 1 is equal to 2. If the first one can vary in the range of -0.1 to +0.2, in other words, if the distribution has a range of 0.9 to 1.2. If the second one can vary in the range of -0.2 to +0.1, in other words, if the distribution has a range of 0.8 to 1.1. Which can be calculated as a distribution with a range of 1.7 to 2.3, where the sum can vary between -0.3 and +0.3 for the total of 2. Then the sum can be extended to distribution arithmetic. If the multiplication is 1 times 1 equals 1, then as before, if the first one has a distribution of 0.9 to 1.2 and the second one has a distribution of 0.8 to 1.1, then the product can be expanded to a distribution with a range of 0.72 to 1.32. This operation not only determines the range of variation, but also the profile of the probability value of the distribution of the operation result as the most likely distribution from each of the original distributions. In dealing with variation, this mathematical extension is defined as the 4 arithmetic operations in 1 to 3 dimensions and integrals that find solutions to various simulations and differential equations. Obtaining the distribution shape after calculation makes it possible to use various judgment indicators. For example, by obtaining a distribution with performance as a parameter and a distribution with the target as a parameter in the same unit, the product of the probability distribution of performance and the cumulative distribution of the target has an area that is the probability that performance exceeds the target. This is a distribution that determines the probability that performance actually exceeds the target. This is the probability that the two distributions come within a specified distance. For example, the probability that a shell will hit a target can be obtained. This is by arranging the two distributions accumulated in the negative and positive directions. For example, the price or sales volume at which supply and demand are balanced can be obtained. In this way, it becomes possible to make probabilistic judgments about indicators that have large variations and are difficult to judge. Let's clarify how the above methods for dealing with variance fit into existing mathematics. The history of mathematics has progressed by expanding the concept of numbers. For example, the concept of natural numbers, which perform calculations such as 1 plus 1 equals 2, first came about, and the range of applications was expanded by introducing the concept of integers, including negative and zero. Furthermore, concepts such as rational numbers, irrational numbers, and real numbers were born. The method for dealing with variance proposes extending the concept of numbers to distribution and treating this distribution in the same way as traditional numbers. For example, numbers became multidimensional, giving rise to the concept of vectors. As shown here, vector A and vector B are operated on to become vector A plus B. Next, the operation of integration was added to vectors, which developed into analysis, making it possible to simulate phenomena in various spaces. The method for dealing with variance proposes taking multidimensionality a step further and expanding the concept of ubiquity, in which position and velocity are expanded from points to distributions. This is an example of a distribution calculation that calculates a new 3D distribution A plus B from a certain 3D distribution A and another 3D distribution B, and extends a vector into a distribution. The 3D distribution is represented as a heat map and projected as contour lines on each dimensional plane. This is the actual calculation result calculated with the tool. To deal with variance, we propose a method of simulation using distribution by extending distribution calculations into integrals. I believe that in order to perform highly accurate physical simulations, we will need calculations that extend numerical integrals into distribution integrals as a solution to differential equations. I believe that this will achieve high quality in a variety of hardware and software development and physical analysis. The fact that the accuracy of calculations can be improved by dealing with variance predicts that current mathematics will need to continue to be improved. This means that mathematics is originally a tool that only approximates the real world, and that we cannot use it as a black box. We will be deceived if we do not use it carefully, taking into account the purpose of its functions that have been improved in the past. This is a warning against the recent trend of thinking that mathematics, in cooperation with physics, is an all-purpose tool that can reveal all the secrets of the universe that we cannot see. Gödel's incompleteness theorem is said to be a theorem that denies that the universe can be explained entirely by mathematics, and that mathematics is an all-purpose tool. I believe that mathematics is a collection of tools with various different purposes to simply express reality. The history of mathematics is a history of patching them together to make them consistent. For example, I believe that addition and multiplication are originally different tools with completely different purposes. Professor Mochizuki of Kyoto University introduced a new mathematics called interuniversal Teichmuller theory to prove the ABC conjecture, which defines the relationship between addition and multiplication. This can be understood as a reason why a different tool was needed to convert between tools that have different purposes in order to explain the relationship between them. Similarly, the method for dealing with variance can be thought of as a patch to mathematics to accurately model the real world, which includes variance. The real world is even more complex, and I believe that in addition to variance, it contains various structures that we are currently unable to recognize. Therefore, I think that in the future, in order to deal with various structures, we will need a variety of different mathematics depending on the purpose. The method for dealing with variance is one such mathematical patch. Nature is said to be simple and beautiful, but in reality it is only simple in the way that it can be expressed in mathematical formulas, and as long as it is clear that the solutions are only probabilistic, I think that nature's beauty remains hidden behind a veil. For details on how dealing with variance, I have published a book and have made several tools available at the address shown here after the book was published. Please use the tools to experience for yourself how dealing with variance can achieve high reliability. Thank you.